All right, we're back with video two, dealing with derivatives. This particular video is going to talk about tangent lines to graphs and how to find them using limits, and then also how, again, that relates to instantaneous velocity of an object. And then again, really what the definition of a derivative is using limits. So, okay, first of all, we're going to talk about something you should be familiar with, but you might not have thought about in a while, and that's the idea of a secant line. So, you learned that secant lines in geometry should intersect your graph twice. So, you did them with circles, but you can do them with any graph. So, if you'll notice, this teal line that I've got here is a secant line to this blue graph. It hits my graph in two different places, right? So I can find the slope of that secant line pretty easily. It's just slope. So it's if this is A where it hits it and this is B, then technically like this point is A, comma, what I get when I plug in A, f of A. And then this point would be at B for the X value, and then whatever you get out when you plug in B. So this shouldn't look that crazy as far as slope goes. This is just the formula for slope. So once again, your rate of change, or this is also known as average rate of change. So your rate of change is y minus y over x minus x. Pretty straightforward. That's average rate of change. So let's look at an example of that. So if I ask you to find the average, that's important, rate of change for this function on this interval. Now, you have to be careful because this interval has brackets, so it's very easy to tell that that's not a point. But every once in a while, it will give you parentheses, and so you just need to know that when I'm talking about an interval, I'm talking about an interval of x values. So if I want to know the average rate of change, and this is basically asking me to look at what the slope is between x equals -1 and x equals 2. So if I could find the points that my graph are at -1 and 2, then I could just find the slope between them. So we actually have to plug that -1 in. So I'm going to plug in -1 here. And when I plug in -1, I end up with 1 minus 1. So I get 0. And when I plug in 2, I get 1 minus 4. So -3. Okay, so if I want to find the average rate of change between those two x values, then I just need to find the slope of those points. Okay, here we go. Slope, change in y over change in x. I've got -3 minus 0 over 2 minus -1. Just be careful you include the subtraction. Okay, so I have -3 over 3, so my slope through those values, or for that particular interval, would have been -1. Okay, so that's the typical slope that you've been comfortable with since you've been learning algebra. Let's talk about now what we were trying to get at yesterday, which is what if I don't have 2 points, right? What if I just want the slope perfectly through one instant, 1 point, right? So I want to know how fast you're going. That's another way of thinking of slope, your rate of change at that particular 1 point. So this can be a little tricky. So let me break this down a little bit. So let's imagine that we've got our curve. So here's just the same type of graph, and I want to find the slope through that point. Well, I can draw that in. So I'll go ahead and draw. That is terrible. I'll go ahead and draw in my tangent line. So if I wanted to find the slope of something that was close to it, I could pick another point on the line and I could draw and find the slope of the line that goes between those. And what you'll notice is if I keep picking points that get closer to the original point, I guess I'll just call it A, then my slope between those is going to get closer and closer to almost perfectly being that tangent line, right? So if I could let these 2 points be really, really close together, then I could find a more accurate version of the slope. But of course, in math, we don't want to just get close enough. We want to get the actual value. So you learned a way in the last unit to let something get smaller and smaller and smaller, and that's called the limit, right? So here's what I'm going to do. I'm still picking 2 points. Okay, so we'll say that this point right here on my x-axis is A. And then I'm going to let this next point that I'm using to find slope, I'm going to let it be A, but just a little bit more. So I'm going to call that little bit extra H. And so again, if I add like point 1 to A, then I'll get 2 points that are point 0.1 away from each other. And so that'll be pretty close. But what if I let H be like 0.001? Then they'd be even closer together and my slope would be more accurate. And what if I let it be really, really small? In fact, what if I let H basically get closer and closer to being 0? That would make these points basically become on top of each other, but I would still be able to get the slope. So that's what we're doing. So we're going to find the slope using these 2 points, but we're going to let h get closer and closer to basically being nothing, which would put the 2 points right on top of each other. So what would that look like? Okay, well, the slope, again, would be the y values, change in y over change in x. So change in y would be, this is, let's see, when I plug in this value, a plus h, that would be the first y value, minus what I get when I plug in my other point, f of a, over my change in x's, which would be, here's my x value, a plus h, minus my other x value, a. Now, the cool thing is on the bottom, the a's are going to always drop, and so you just get an h on the bottom. And remember, the whole idea here, though, is that if we want to find the slope through just one particular point, we basically want our what we're adding to be 0. We want it to end up being on the same point. So that's where the limit comes into play. So this gives me, it's an equation for slope, guys. It's just reduced. And we're saying let the distance, let what I'm adding in between basically become nothing, so that we'll just find the slope through that particular point. This is instantaneous rate of change. You're going to hear me talk about it so much for the entire year, but I just want to give you a little in-depth look at where that comes from. Okay, so let's look at our first example. So in this example, we want to find the equation of the tangent line to the graph through this particular point. So this particular graph it's a quadratic, and if we're looking at -2, 4, we might end up somewhere like this. And so we're looking at the equation of the tan line through -2, 4. Okay, to write the equation of a line, first of all, this should come back from Algebra 1. We need the slope through for that line, and then we need a point to go through. A point to go through is actually pretty easy. We know this point we're using is on the red tangent line, so we can use the point -2, 4. We're just going to need the slope. Just to give you a heads up, we're going to use, instead of using y equals mx plus b, which you can, we're going to use point slope form a lot more often in calculus. Point slope form looks like this: y minus the y value of the point equals the slope times the x minus the x value of the point. And you'll see that in just a second. So we need the slope of this tangent line. Well, you guys know that the slope of that tangent line is that limit, that derivative that we looked at. So that's what we're going to do here. We're going to find the limit as h approaches 0 of f of x plus h minus f of x all over h. So here we go. So that would be the limit of, if I plug in an x plus h for x, I end up just with x plus h instead squared, minus, what do I get when I plug in x? Well, that's easy. That's just x squared all over h. Now, you did this in the last unit. If you multiply all this out, the x squareds end up canceling, and you end up with something that's like 2xh plus h squared over h, and then you end up being able to factor out an h, and so you end up with the limit as it approaches 2x plus h, and then you plug in 0, and you just get 2x. So here's what this means. This is the slope, but it's the slope depending on what x value you want to look at. So in our case, we want the slope through the x value of -2. So if I want my particular slope, I'm going to plug in the x value of -2, and that means we want to use a slope of -4. So let's write our equation. So if we go over here, we're going to use the point -2, 4. So y minus the y value, careful not to mix up x and y, equals my slope times x minus the x value, which minus a negative would become +2. Boom. There's the equation of that tangent line at -2. Okay, so we're also going to relate this to velocity. Velocity is speed, and speed in general, you guys know as the distance you travel in a particular time. So average velocity will be when I find the velocity between 2 times, and then instantaneous velocity will be the speed at a particular moment. And so that's where we're going to use our derivative or our limit that we've been learning. So let's look. So in this scenario, we have a sandbag. It's being dropped from a hot air balloon. We know that it's hovering at a height of 512 feet. And as it falls, it follows this equation. So the height that the sandbag is S of t given a particular amount of time that's passed. This is gravity's effect. This is the initial height. That should look familiar from stuff you've done in Algebra 1 and Algebra 2. But here we go. if we want to find the velocity, first of all, velocity is speed, and we know, or slope, right? And so we know if we want to find the slope, but at an instant, we're not doing average velocity, we're doing instantaneous velocity, then we need the derivative, or we need to use that limit notation. So if it wants me to find the velocity for any particular value of time, so any a, that's when I'm going to treat it like a true limit. So here we go. That means I want the slope, so I'm going to do my limit. I'm going to do of a plus h, because this time I'm looking at a, minus f of a. This is just that definition, guys, over h. So I'm actually going to plug in a plus h for every t that I see. So I've got f of, or excuse me, I've got negative 16 times, instead of a t, a plus h squared plus 512, minus what I get when I plug in an a. You better be using that parentheses. And then all of this is over h. And then I can continue to simplify this down. On top, I can tell you that once you square this and then multiply everybody by a negative 16, you end up with negative 16a squared minus 32ah minus 16h squared. Again, that's after I multiply, square this and then multiply, plus 512, and then distribute the negative, plus 16a squared, and then minus 512. And all of that's still over h, and I'm still looking for the limit. Okay, now here's some cool things that happen, right? The negative 16a squares cancel, the 512s cancel, and we end up with this guy. Now remember, the problem with doing a limit is if I actually try to plug in 0 from the very beginning, I get 0 over 0. But from last unit, you learned, oh, I can factor an h out of the top and then cancel it with the bottom. So I really just get negative 32a minus 16h after I cancel that h. So then if I plug in a 0 for h, I get negative 32a. So what does that mean? That means that the slope, or the velocity, will be negative 32 times whatever time you want to plug in. So this answer is negative 32a. And then on the next one, when I actually want to find it at a particular time, now I can just plug in the time I want to plug in. So I end up with negative 64. And I believe my units here were feet per second, so I could get more particular. All right, for the last part, I want to know what the speed is, or the velocity, when it strikes the ground. Well, that's kind of its own little animal. When this sandbag hits the ground, I have to go back to the original equation because I want to know when the height is 0. So I'm going to have to set my initial equation, which gave me the height, equal to 0. And then I can figure out what time that relates to. So if I solve this, I think this ends up being 32 here. And when I square root that and simplify, this simplifies to 4 root 2. So that means I know it's going to hit the ground at this time. And now I have a relationship for speed, or velocity. I just have to plug in the time I want to find it. So I'd have negative 32 at the time of 4 root 2 should have a speed of negative 128 root 2 feet per second. And of course, if you want the decimal, you could plug that into a calculator. Okay, so let's look at our last example. This last example is talking about voltage and a current and resistance, and it gives us the relationship for that resistance compared to a particular current L. It wants us to find the instantaneous rate of change of the current with respect to R. And so it basically wants us to find the velocity, or again, this derivative or limit. So first I'm going to do it for any R. So I'm going to find the limit. I'm basically finding the velocity, but I have to do the limit. So I'm going to do, again, of f of R plus h minus f of R over h. That's just that definition. So then I'm going to plug in R plus h for every R I see in my equation, and then just minus f of R, so 100 over R, and all of that is still over h. Okay, then I'm going to make common denominators, which you learned how to do in the last unit. So my common denominator here is R times R plus h. So this guy gets multiplied by an R, this guy gets multiplied by an R plus h, and then all of that is still over h over 1. I'm going to distribute that. On top, I end up with the 100 r's cancel, and I end up with a negative 100h over r times r plus h, and then technically times 1 over h. The h's are going to reduce, and when I find the limit, when I let h actually get towards 0, then that means that this h here would become a 0, And so I just end up with negative 100 over r squared. If I wanted to find that a particular resistance of 20, I'm literally just plugging in 20 for r. So for B, I have negative 100 over 20 squared, which is negative 100 over 400, or negative 1/4, or negative 0.25. Good luck on the homework.